Well, everyone, welcome. Thank you all for being with us today. We're excited to be part of this group and part of this conference. My name is Dr. Kristen Miller. I'm an associate professor at the American Public University System, and I'm also the co-advisor of the our chapter of the American Institute of Aeronautics and Astronautics for APUS. I'm excited. I'm going to be talking to you today about a student research initiative here at the university. Following me will be Todd Barber. We have an excellent panel today. We have Todd Barber, who's a senior propulsion engineer at NASA JPL. He worked on Cassini, which I have to tell you is my personal favorite mission of any mission that NASA has ever done. So I'm really excited about that. He's also worked on several other, the Mars Exploration Rover, a Deep Impact. He has an excellent bio if you want to peruse it. We have Peter Martinez, who is the Executive Director for the Secure World Foundation and chair of the UN Committee on the Peaceful Uses of Outer Space Working Group on Long-Term Sustainability of Outer Space Activities. So we're super excited to have him here with us as well. And the format is we're each going to give a presentation, and then we will save questions at the end. So please drop your questions into the Q&A. It's a little easier to monitor that than the chat, and we will take those at the end. And with that, I'm going to go ahead and start sharing my screen. Here we go. So I'm here to tell you about an initiative, an education initiative that we've implemented at the American Public University System. It's a supernova search program. As you've heard at this conference, APUS is a completely online university, and as such, it is extremely important to us to find ways of providing authentic and hands-on learning experiences, and especially research experiences for our students. And this program is one way that we do that. So what are supernovae? Just a quick overview. They're incredibly luminous stellar explosions. They can occur usually associated with the deaths of different types of stars, but they always involve a catastrophic release of energy. There are two different types of supernovae. There are thermonuclear supernovae and core collapse supernovae. Thermonuclear supernovae are known as type 1a. They have peak luminosities of about 10 billion solar luminosities. That is equal to about 10 to the 44 joules. It's approximately the same amount of energy as the total output of the sun during its entire 10 billion year main sequence lifetime. But it occurs over a period of just a few weeks. So it's an incredible amount of energy in a very short period of time. Part of the reason that they're so very bright. Core collapse supernovae. There are three different types: type 2, type 1b, type 1c. These are different types which depend on what happens to the envelope of the massive star during the explosion, whether they have the hydrogen envelope, whether they have the helium envelope, or whether they've lost all the layers before the explosion. It's mainly distinguished by differences in the spectra. All of them peak at approximately 1 billion solar luminosities, so about a factor of 10 lower than the thermonuclear supernovae. They, however, are visible for longer time periods, over a few months. They have a plateau that is due to the cooling of that envelope that's blown off. Just to give you a little bit of background, thermonuclear supernovae, approximately maybe somewhere around 50% of all stars form in binary systems, and binary systems that many of these binary systems are close binaries, and they involve stars of different masses. When you have stars of different masses, one star is going to evolve much faster than the other. It will become a white dwarf while the other star is still in the main sequence, and when its companion reaches the giant phase, material can be transferred through the Roche lobe, through the Lagrange point. And this hydrogen-rich material that is the former envelope of the companion star, it builds up on the surface of the white dwarf. So it's in a degenerate environment. This leads to recurrent novae, and when the Chandrasekhar limit is exceeded, then a supernova results. Core collapse supernovae, on the other hand, are associated with the deaths of, oops, I did not mean to do that. It is associated with the deaths of massive stars, which undergo many different cycles of fusion in their cores. That's all well and good until they get to iron. Fusion of iron is endothermic, so it pretty much doesn't happen. The loss of the energy source means a loss of hydrostatic equilibrium and the collapse of the core ensues. The conditions in the core become degenerate. The outer layers, as they compress the degenerate core, the situation gets even worse when large amounts of energy are carried away by neutrinos, and a supernova explosion results. It's basically a shock wave that propagates to the outer layers, and this is where we get creation of many heavy elements and neutron stars and black holes forming. So just quickly, the light curves that we see for supernovae, again, the yellow is the type 1, the much brighter, and then the other 3 colors represent the core collapse supernovae, but they're all extremely fast, extremely light events, which means that they're very easy to observe at large distances. And I just have an example down here in the left corner of before, and on the right-hand side an after picture, and you can see that little supernova that appears, and it's extremely bright, which makes it really easy to detect and to detect through a visual analysis of the images. Why do we care about detecting them? There's 4 main reasons that supernovae are important to us. The first is in galactic distance measurements. So they're what we call high Z supernovae, which are supernovae that occur in galaxies at high redshift. They're very useful as standard candles. They can be help us find very accurate distance measurements, which help us to improve our value for the Hubble constant. It relates to determining the rate of the expansion, which has implications for dark energy and also the size of the universe. The second main reason is that they give us an increased understanding of stellar evolution. Both types of supernovae occur towards the end of star lifetimes. The type 1 deal with binary star mass exchange. Both of them help us understand degeneracy forces better, explosion physics and nucleosynthesis modeling. The third reason that we study them is because supernovae enrich the interstellar medium. Pretty much every element besides hydrogen and helium are formed within stars, and most of the heavy elements are formed within supernovae. If you just drew up this little picture of the periodic table showing the origin of the solar system elements, and the green and the very light blue come from the 2 types of supernovae. You can see how many elements we have today, elements which are essential for planet building and for life itself, and they all come from supernovae. So it's important to us to be able to figure out the rates that they're produced in supernovae and also how they're distributed through the interstellar medium. It has implications for planet formation as well as cosmic ray production. There are also unusual supernova profiles. So most of them follow the profiles we looked at before, but we're finding some that don't, that have oddities, that don't fit our models. And understanding the exception always provides more information and greater understanding than the ones that follow the rules. But we need more studies in order to be able to do statistical analysis on these unusual supernovae and come to a greater understanding of them. So even though we've discovered many, many supernovae, it's important to keep discovering them and to keep building our base so that we can understand all the many different types of supernovae. We're still at the point where we're gaining a lot of knowledge from every discovery that's made. So what are our chances for detecting a supernova? It's always good to know if you have a shot before you try to start a research program. The rate for the Milky Way is fairly well determined. Most groups agree. It's been measured by several different groups, and the numbers all come out to be about 1 supernova per 50 years. We assume that this is pretty typical in the universe. If you just assume it's absolutely typical and you do a back of the envelope calculation and apply it to every galaxy, every spiral galaxy out there, then you figure out that there's basically 1 supernovae per second in the universe somewhere. They're random events though, and many are obscured, hard to detect. So the detection rates are not quite that high, but they're at least occurring, so we have a chance. The Lick Observatory did a nearby galaxy supernova search to try to determine some very accurate estimates of the supernova rate in the universe for nearby galaxies. So I'm not looking at the high Z supernovae, and this is applicable to our sample. They came up with a volumetric rate that I have here for the different types of supernovae. And when we apply this to the volume that our sample represents, then we come up with roughly 1 to 2 supernovae per year, depending on the type that you're detecting, which is encouraging, right? Now, our sample, this is only valid if the sample includes every galaxy in that volume, which ours won't, but it's still an encouraging number and an indication that we have a chance of finding them. If we compare with other supernova search programs, the programs that are comprised of just individuals searching for supernova, they typically report rates of 1 detection per 4,000 to 5,000 images analyzed, whereas small groups that work in teams, so they have access to maybe 5 or 6 telescopes for the observations, they tend to find 1 supernova per maybe 2,800 images. And this tells us that with given the parameters of our program that we have a good detection, we are in line to discover a supernova every probably about once a year is probably a pretty good average for us to shoot for. But supernova searches, because these are random events, they require frequent monitoring, a large galaxy sample. It means that you have large amounts of data and large amounts of data analysis for detection, which makes them an excellent group project. And that brings us to our project. The thing that is unique about our project, so I mentioned that there are many people doing supernova searches out there, both amateur and professional, and as well as academic. But the thing that really distinguishes the APUS program is that ours is a student-designed and student-run initiative. So it provides a research experience and a leadership experience for our space studies students. In the past, we've had a couple of lead graduate students who designed the initial project and did the beta testing for it. The current team, lead team, they gain experience designing and implementing a complex research project. They gain experience leading team-based research. They learn to motivate consistent and timely participation, which I always say that's a really easy phrase to say. It just rolls off your tongue, but actually achieving that, right? That's quite an accomplishment. They troubleshoot and resolve any problems that arise, and they gain real observational experience. So there's incredible benefits for our team. We recruit for this program from all of the APUS space studies students, both undergraduate and graduate. Every student has the opportunity to work with real telescope data. They gain an authentic data analysis experience using programs that are standard for the industry. They learn about supernovae from actual research experiences, not just from their classroom, and they have an opportunity to be part of search and discovery, which is the exciting part of the program. This program is possible because the university owns and operates and maintains a research-grade telescope in West Virginia. There's a picture of our dome on top of the technology building. We're at an elevation of about 170 meters. It's a 24-inch diameter mirror plane wave telescope with an equatorial mount. The telescope is fully robotic and able to be operated completely remotely. It can also incorporate completely autonomous scripts. And this makes it so that our group is able to use it no matter where our students are located and be able to observe frequently the scripting. We image galaxies in 6 different regions of the sky. We look at galaxies of 11th magnitude or brighter. There's 177 galaxies to go in total in our sample size. That's about our limit of how many we're able to image per night. And we have, currently we're using a team structure for the program. We have a leadership team, and then we have what we call the Blink group. The leadership team is comprised of our lead researchers, Jason Bouchard, who's an APUS Space Studies undergraduate student, and Terry Trevino, who's a master's student and also our observatory assistant. We have a detection verification analyst on the team. That's Christopher Colvin, who's an undergraduate student. And we have a supervisor, Melanie Kristen, who was a former lead graduate student with the project and is now the education director of the Perry Research Institute. And at this point, I'm going to ask that we turn that we bring my my lead researchers on. They're going to tell you a little bit about the program themselves. Daniel, if you can bring them on now, that would be fantastic. Do I need to stop sharing my screen to do that?
You can continue sharing your screen. Terry and Jason are on now.
Great. All right, so guys, take it away.
You first, Jason.
Greetings, I'm Jason Couchard, one of the lead researchers, and I'm covering the topic of team structure. So with that, I'm talking about how we're able to basically put a group into a team and make it more efficient that way. We're enabling them to better, pardon me. We are helping them and training them so that when they take over our position, that they can. And recently it's been coming up a lot where a lot of people have questions, and we'll be out there, both me or Terry, to help them and advise in any way we can. So that way they're not bothering, or not so much bothering, but taking up time from these supervisors who are analyzing and checking things in case it was a possible supernova. Terry, you?
Yeah, the process is fairly simple. We take and use data that Dr. Miller presents us. We usually take a day to turn that data around, sometimes a little longer. We use 2 plates. We'll take a plate that she provides us, plus a plate that we would call like a comparable, and we'll put them together. We'll usually just blink those, and that's how we discover these supernovae. And even, I believe, day before yesterday, we found a transient that we didn't know that we had already taken a photo of months ago, but of course it was already discovered. Anyway, the process works really well. The guys will find something, they'll reach out immediately to either Jason or myself, and then we take that from there. We'll take that up the chain. Chris gets involved should he be available, and we can reach out to him. He's usually quite responsive, and then as well, Dr. Miller is brilliant in terms of getting to us if anything that we find. But yeah, that's it. Super simple. Would love to have all of other students that might be interested. Love to have them on the team as well.
Awesome. Thanks so much, guys. You guys do amazing work. They've got the program running really well, and they've been able to really streamline it and to really upgrade the process. We're almost out of time, but I want to show you here, this is one of our detections. If you look in the red circle, you can see this object blinking. This is actually a known variable star. The program has been operational for just about 6 months now, past the testing stage. And we've had several transient detections, several asteroids, which is pretty cool because those are 16th magnitude. So it's pretty cool that we were able to detect those using this visual method. We've found several known variable stars, and on the next screen, I can show you another little animation showing this is one of our images that we detected. The supernova right there in the middle is easy to see. This was a previously published supernova, but we were able to detect it with our system. So we're in good standing to, our method is robust, and we're in good standing for an actual detection, which would be pretty exciting. Just quickly in the last moment, the detection is the exciting part, and that's and certainly we desperately want to find a supernova and put our stamp on it. But the real value in this program lies in the leadership opportunities that are afforded to the students. The leadership team in particular gains experience in project testing and development, in program management experience. It's a research opportunity for everyone, the lead team as well as the Blink group. They gain hands-on learning and experience with telescope images, and the lead team gains observational experience as well. So we're really excited about this project. I'll just close with this screen, which I won't even really talk about, but I'll just let people look at. We appreciate the chance to tell you a little bit about our project, and I'll drop any interested APUS students will drop the Gmail into the chat so that you can contact us. Terry and Jason monitor that if you're interested in being part of this project. So I'm going to go ahead and stop screen sharing. I think that's my time, and I'm going to turn the time over to Todd Barber, who will to start his presentation.
Thank you, Dr. Miller. My name is Todd Barber, and I am Internet Speed Challenge. So you won't see a picture of me today. I'll focus on making sure I have a good audio connection. Also want to acknowledge Daniel, who will be projecting my Mars Perseverance slides. This is the current Mars 2020 rover en route to the red planet as we speak. We just passed Mars opposition. The closest Earth and Mars will be until 2035. So when the planets align like this, we know it's time to head to the red planet. And I've got about 20 minutes here. I think we've got a little video. We'll see if this plays with the audio. It shows about the last 6 months getting ready for launch. Okay, thank you very much, Daniel. And so here we are. We are basically 4 months away from landing this beautiful big Perseverance rover. And boy, what an apt name. When we had our student naming contest to name the rover, I don't think we ever dreamt of having to try to do so during a global pandemic. It's hard enough to do these missions when things are going well. But trying to fly and land this potentially from home is a new challenge for sure. So next slide, please, Daniel. Okay, we've got a rich history of Mars exploration at JPL and really with NASA. I'm delighted to say we have an international flotilla of spacecraft heading to the red planet at this opportunity. So the Chinese are sending an orbiter, a lander, and a rover. They launched a couple weeks before we did. And the United Arab Emirates are sending their first interplanetary mission, an orbiter at Mars called HOPE. So we're delighted to participate in this international onslaught heading to the red planet in 2020 for 2021 arrivals. So one thing we've talked about with our missions in the past is following the water, because we know Mars was an ancient liquid water world. At the same time, life was forming on Earth. So that drives a lot of what we do. It's just possible that life might have been even more favorable to start on Mars in the early history of the solar system. So we've followed the water with various orbiters. We see across the top, Mars Odyssey, Mars Express, which is a European mission. Mars Reconnaissance Orbiter still going. We can take 1 foot pixels looking down on Mars. So if there's Martians playing beach volleyball, we could just resolve the volleyball. We haven't seen that yet. We'd let you know. I think our funding would be secured in perpetuity, so that would be awesome. MAVEN is sampling the upper Mars atmosphere. ExoMars, I believe, is another European orbiter. So not only do they have their own missions, they serve as relay satellites for many of our landed assets. Then looking back, the Mars exploration rover, Spirit and Opportunity, landed in 2004 for a 3-month mission. Spirit went 6 years into its 3-month mission. Opportunity lasted 14.5 years into its 3-month mission. And that was my first Mars mission, getting to work as a propulsion engineer on those. We also did the Phoenix mission near the pole of Mars, looking for water ice with scoops. We found it. We had Curiosity as well. The Mars rover launched in 2011, landed in August 5th of 2012 for a 2-year mission. We've been driving for 8 years and counting. I worked that mission as well, and tremendous successes on the red planet there. InSight is a fixed lander that measures Mars quakes. We've detected those weeks to get the Mars interior structure. The ExoMars rover is a European. I haven't had a chance to change the date. They had a launch slip for 26 months due to some technical issues and some COVID-19 issues, frankly, that forced them to skip their launch window. But we barely made it with Mars 2020 Perseverance. We were 2 weeks into our launch window and took off for the red planet on July 30th. Because of that launch slip and a short trajectory anyway, we've got a short 6.5-month cruise to Mars, and yet have to do all the same activities we've done on prior Mars rovers. And that's been a real challenge. We also went into safing mode, where the spacecraft kind of halts everything and is temporarily in trouble and goes to power positive, turns off science, things like that. That happened 3 times in the first 16 days. So we were asking for it, naming a mission Mars 2020 and launching, you know, during a pandemic year. But we've recovered there. We're on the way to the red planet. We've done 2 of our trajectory correction maneuvers, well on the way to Mars. Next slide, please. Okay, so we've got this history or proof that Mars had water in the past, and it's not just because things look like dried riverbeds and lake beds, which they do, but we also have the mineralogical evidence for chemicals, minerals that could only have formed in liquid water. So the basic building blocks were there. Mars lost its water, it went underground as ice, the atmosphere sublimated away. There's an ultraviolet light beating down, no ozone layer to protect Mars. So, you know, life on the surface today is not that likely. But if it ever formed, perhaps it followed water underground. There may be liquid water underground. We have some evidence of that as well. So we're not going for the home run, looking for life here, but certainly the conditions of biology, ancient habitability, and it's very exciting to have Perseverance on the case. Next slide, please. Okay, I'll skip that just in the interest of time. So it's really nice having this rover. It's like having a robot geochemist and geologist all wrapped up in one. And one of the most exciting things, this is the first step, if you build it, they will come, in a Mars sample return campaign that NASA has been wanting to do for decades. And the first step is let's collect the samples. So we will cache them, CACHE, in titanium hermetically sealed test tubes, dozens of them, to be dropped on the Martian surface, ready for a future fetch rover to pick them up, to place on a MAV, Mars Ascent Vehicle, which is yet to be built, to blast into Mars orbit, to meet up with an orbiter that hasn't been built yet, that will then come back to the Earth and deliver these pristine Mars samples. So this is the first step in that long, exciting campaign to bring back Martian samples to Earth. Next slide, please. So what's beautiful, you know, we can do pretty good chemistry and geology on the surface, but we're limited by the mass, power, and volume that we can launch on a spacecraft. The beauty of bringing samples back, and we're talking about 1 kilogram or less here, we can divide it up very finely and send it to all the best researchers all around the world and put all of Earth's assets into understanding these ancient questions of habitability. So that's the excitement about picking a great landing site and bringing samples back. Next slide, please. So we're going to look for biosignatures on the planet itself. Now, Occam's razor says the simplest explanation is probably the likeliest. And I also love the Carl Sagan corollary there is extraordinary claims require extraordinary evidence. If we see little wiggly things that look like fossils, you know, that we wouldn't necessarily jump to the conclusion that life started on Mars. However, we do have examples on Earth of things that Occam's razor still tell us that the most likely explanation for the things we're seeing are life. So we will not hastily jump to that conclusion on Mars, but it's exciting to have the payloads on Perseverance that can actually do this kind of analysis on the red planet. Next slide, please. So where do you land this beautiful rover once you've built it? Well, we looked at 100 landing sites and whittled it down to some candidates, but we settled on one called Jezero Crater, and we love this. we have what's called the landing ellipse. That's a 3 sigma landing ellipse at left. And what that means is 99.8% of the time I'll guarantee we'll land within that ellipse. And it's a little hard to tell, but to the left of that ellipse, that's a flood plain coming out of like a river delta. So this was a warm, wet place on Mars billions of years ago with rocks that flowed down those canyons and out. So this, and we have mineralogical evidence that this was a place abundant with liquid water as well. It's kind of fun with the landing ellipse. We've shrunk those over the years. They used to be huge, and the engineers and scientists have completely different goals. The engineers want to land in the most flat, boring, safe place where there's no science. And scientists want to land in places that give engineers heart attacks, you know, top of huge mountains, inside Grand Canyons and cliffs, and go rappelling and all these kind of things. So the beauty of shrinking the landing ellipse is we can keep the engineers happy and safe, and yet find a place that's super scientifically interesting, as Jezero Crater is. Next slide, please. Okay, this is, I basically tipped my hat there, but in false color, it shows really well there how this is, it looks like the Mississippi River Delta here. And some of these rocks date back to nearly the formation of the solar system. So that's exciting. This is when Mars had liquid water, and perhaps life started there as well. Next slide, please. So this is an example of where we might land and what our first traverse map would be. We'll drive up that delta. You know, we'll be reactive. We'll have a lot of fun planning the mission and doing some autonomous driving with some artificial intelligence, as well as controls from the Earth. To do this, you have to get a Mars driver's license. It's much harder to get than a California driver's license. I assure you there. And then, as it turns out, there's a gender difference in Mars rover drivers. One gender is better than the others. And I won't make you guess. The answer is women. And the reason is, I always, in a live presentation, I would ask for guesses on why that is. Someone said it's because less road rage. Not a lot of road rage on Mars. We're fairly alone there. It's really the patience, because for every man that's driven, if you've been stuck in sand or mud or snow or ice, what does our male brain tell us to do? Hit the gas, that's all it needs. And of course, we get further stuck. So the patience and deliberateness for our female rover drivers makes them superior. Next slide, please. So the rover itself does look kind of like a twin of Curiosity, Mars Science Laboratory from 2012, but there's 4 new sets of things I like to talk about. Next slide, please, that make it different, Perseverance. So we have 23 cameras on board, and lots of Kodak moments everywhere. So there's stereo cameras, so you can Google Mars 3D. There's cameras, microscopic imager cameras on the robotic arm. We have hazard avoidance cameras at the front and rear, navigation cameras. It's a lot of fun there. We also have a pulsed infrared laser that can vaporize rock from 30 feet away. So if we get within 30 feet of a rock wall, we zap the rock, the gas cloud comes off, we measure the composition of the rock with chromatography. So the question I get from the kids is, would this hurt you? Because we also have the same laser on Curiosity. So I found the principal investigator that built it and asked him, and he said, well, it can vaporize rock from 30 feet away. What do you think, Einstein? So, you know, we tell the Martians, we come in peace, but we are armed. We have a Martian death ray. We will use it if attacked. Next slide, please. So SuperCam, there's the laser that comes out of SuperCam. Next slide, please. So this is very exciting. We have 2 microphones on board. So not only can we hear the ambient sounds of Mars, we'll hear the vehicle going through its paces. What a wonderful way to bring our visually impaired taxpayer and student along this beautiful, amazing journey that is planetary science. That's the good news. The bad news is we've sent 2 missions before with Mars microphones. Both missions failed. What don't the Martians want us to hear? I really want to know. So hopefully the 3rd time is the charm, and we will be able to check out the sounds of the red planet. Next slide, please. Now we have bicep curls. I think the video should play here. We're doing our curls in 1G gravity before Mars 3/8 gravity will be easier. We can scoop, drill, study rocks. It's really exciting to have a robot geologist on the red planet. Next slide, please. It's still showing the last one here just because of the video, I think. So I'll talk about what's coming next. One thing I haven't mentioned is we have a, oh, here we go. Sherlock and Pixel, we have rock analyzers, so we can tell what compounds are there, what molecules are there, what atoms are there, their isotopic ratios, which tells us something about Mars history and the age of the rocks. We can measure the pH, we can tell if they're hydrated, and it's just tremendous having this robot geochemist and geologist ready to go, assuming we stick to landing. Next slide, please. So under the belly of the rover are these caching tubes, and we will, basically pull them out, collect the samples, and drop them for a future fetch rover to pick up samples. And it's exciting having dozens of opportunities to get the best samples for a Mars sample return campaign. Next slide, please. Okay, this is very exciting. We have a technology demonstration called MOXIE, where we take in the carbon dioxide atmosphere and convert it to oxygen, so Matt Damon and others can breathe there in the 2030s. Now, we're actually not storing the oxygen. We're only making about 1 gram per hour, but it's a technology demo for future human spaceflight. Also, oxygen would be very useful to have for robotic missions. We could combine it, use it as an oxidizer and rocket fuel for the Mars Ascent Vehicle, for example. So stay tuned to make sure that works. Next slide, please. Now, as wonderful as all these new technologies are, there's something even sexier that the public just absolutely loves, and myself included. We have a helicopter called Ingenuity that rides under the belly of the rover. We'll drop it down. It'll do little flights on the red planet the first month of operations. So it has a camera. We can look down and see the rover, and this will be the first powered flight on another planet. And imagine the aerodynamic challenges of flying a helicopter in Mars atmosphere, 1% of the pressure of Earth, a cold carbon dioxide atmosphere. It's like flying at 100,000 feet at Earth. So we found a way to do it, and we tested it in a vacuum chamber here. And the short answer is you need long, thin, counter-rotating rover or rotor blades that go very fast, high RPM, and keep the mission lightweight, a good battery, and hopefully it works. We'll have, what a Wright brothers moment to have powered flight on Mars. Next slide, please. So this is the rover upside down, and there's the helicopter under the belly of the rover. You can see the long rotor blades there in our clean room facility. Next slide, please. So we also have a radar that can look beneath the surface, so sand, rock, and ice. I'm not sure what the depth of this is, but it's exciting to be able to use radar to penetrate below the surface. Next slide, please. Running out of time, as I always do on these talks. Launch window opened July 17th. We had some launch delays due to technical problems and some COVID cases at KSC. And then, but we did get off the pad beautifully July 30th, and we're on our way to Mars. And touchdown will be 12:30 or so p.m. Pacific Standard Time, Thursday, February 18th, 2021. So mark your calendars, about 4 months from this weekend. Next slide, please. So we do 354 million miles on the way to Mars. We'll go 13,000 miles an hour and then have to slow down to 0 in 7 minutes. That's why we call that the 7 minutes of terror. Next slide, please. So we'll take photos, and we actually have a controlled landing. So it's more of a precision target landing. That's why that ellipse is so small. So this is something new and kind of scary, but hopefully it will work when we try it out on Mars. Next slide, please. So we have this crazy sky crane and descent landing. We lower the rover on cables. do a soft landing. You lay the rover down more gently than you put a baby down in a crib, if all works. Cut the bridles, the cables, and then the descent stage goes and crashes. Sorry about the Martian stage jump. Next slide, please. So 2 miles an hour. That's a nice gentle landing, if it works. Next slide, please. I think I'm close to the end. So 1 Martian year is 2 Earth years. That's our prime mission. Of course, we hope to go much further than that as we explore the red planet. Next slide, please. So we're in a very diverse landing site that was warmer and wetter. We're going to seek the signs of ancient life. We're going to do the first step in the Mars sample return, and then with the making oxygen, pave the way for future human exploration. That may be it. Next slide, please. Ready to roll? Just a video. Let's do next slide. I don't want to cut into any of Dr. Martinez's time. That's it. Thank you very much for your attention, and go Perseverance.
Thank you so much, Todd. That was fascinating. Peter, you want to go ahead with your presentation?
Can I start, Kristen?
Yes, I'm sorry. Yes, absolutely. Go right ahead. Thank you.
Okay, thank you. Well, that was a great talk, Todd. Enjoyed it very much, and we'll keep holding thumbs for a successful landing on the red planet next February. So thank you very much for the invitation to speak at this event. My name is Peter Martinez. I'm the Executive Director of the Secure World Foundation. We are a private operating foundation based here in the United States, but with an international footprint. We work in the area of space sustainability and space security with the objective of keeping the space environment an environment that is safe and stable for peaceful uses by current and future generations and of all nations. And we work with governments, industry, and academia in support of these objectives. So I was asked to speak to you today about the work that I did at the United Nations on the long-term sustainability of outer space. And so I'm going to just share my screen here. Do you see my slides?
Not yet, no. You have to choose it and hit share. Did you do both? Oh, there we go, perfect.
Okay, all right, great. So let me, hopefully you see my cover slide there. So I will be speaking to you about the role of the United Nations in space diplomacy. But before doing that, let me just provide some context for what we do. So this is the kind of image that most people think about when you talk about space exploration. They'll think about astronauts, the International Space Station. They'll think about exciting planetary exploration missions or the Hubble telescope. And of course, space science has expanded our view of the universe tremendously in the first 60 years of the space age. But of course, the planet that matters most to us is the one that we actually live on. And indeed, many of the, in fact, most of the space missions that are in orbit are put there to provide services and data to people living on the surface of the Earth. And so this is a case of using space to benefit humanity and to support human and environmental security, sustainable development, and so on. And so we have come to rely critically in our daily lives on many of the benefits that space services provide. This is a typical street scene from New York, Wall Street, showing the many ways in which space technology is used to support distributed networks like cell phone networks, financial transactions, navigation, and so on. And so we are, of course, aware of this in the developed countries, but I just want to make the point that developing nations are also very, very reliant on space technology. This is a street scene, I believe, of somewhere in India, but you will see similar scenes in many other developing countries around the world where space technology touches the daily lives of billions of people around the world every day. And of course, we're seeing a space economy that is rapidly increasing in value. In 2001, the space economy was valued at around $64 billion. This report by Bryce that came out a few months ago rated the world space economy at around 366 billion. And there are studies that show that the space economy has the potential to increase to over $1 trillion in the coming decades. This is a slide that shows the which sectors of the space economy are increasing. And you can see here, for example, things like the consumer broadband is an area that's increasing, and then also other impacts, additional downstream services that are based on assets and systems in space. And I'll come back to those in a short while. So at the dawn of the space age, we had a sort of a pristine orbital environment around the Earth, and people could launch objects into space without really worrying much about the risks of collision. But you can see in this in these slides that as we go through the decades of the space age, that the space environment has become more crowded. You see on the left the low Earth orbit environment around the Earth. On the right-hand side, this is a bit of a further away view. You see the geostationary ring and also lots of highly inclined orbits. And you can see that, of course, these dots are not to scale. They're just showing the positions representing the space objects in catalogs. And I should emphasize that these diagrams only show objects that are larger than about the size of a coffee mug, because those are the things that our systems have been able to track for the last few decades. There are new systems coming online that will have the capability of tracking objects significantly smaller than 10 centimeters. And then these diagrams will be completely crowded out with cataloged objects. So what are all these objects? Well, it's a combination of upper stages of rockets, defunct satellites, and also fragmentation debris. This is where satellites, materials in space tend to age. Sometimes things break off, or you have upper stage rockets upper stages of rockets with fuel that are sloshing around and sometimes explode. You also have what's called mission-related debris. These are things like mirror covers and so on that were cast off at some time in the past and are still in orbit. Now, one of the things is the space arena is changing dramatically. This slide shows the composition of the spacefaring countries, if you like, in the mid-1960s. And you can see it was pretty much the United States and the former Soviet Union and a few allied countries, but really dominated by the two superpowers. Fast forward to 2016, and you see the picture has changed completely. There are now many more countries that are active in space exploration, and with very diverse levels of capability. And this slide, actually, if you were to update the slide, there would be quite a bit more orange on the slide showing a number of new countries, new entrants into space activities. So space is becoming much more global than it used to be. We're also seeing the emergence of new kinds of space actors. In the early days of the space age, military activities dominated, and also, as I said, the two superpowers were the main space actors. But beginning with the early 1970s, we started to see the emergence of other countries as active players in space activities. And this is shown with the yellow band on this slide that you can see gradually increases from left to right. We also see the emergence of the non-governmental actors, the private sector. This is the green band that you see at the top of these curves. And this is the sector that is growing most rapidly at the moment. So although international space law focuses on states as the primary actors, in fact, we are seeing the private sector being the dominant space actor, or emerging as the dominant space actor. And so this affects the way that multilateral space diplomacy is conducted and who participates in discussions. We're also seeing new kinds of space activities that were not envisaged even 20 years ago. Things like on-orbit satellite servicing, mission extension, on-orbit refueling, active debris removal. These are all things that are being actively discussed by a number of groups around the world. And these raise concerns. These technologies, by the way, would be foundational technologies for a future trillion-dollar space economy. But they also raise concerns because these technologies could also be weaponized for counter-space purposes. And so there are discussions in the United Nations around both of these aspects, which I will touch on shortly. Another issue that countries are worrying about is orbital congestion. This is a slide that AGI prepared showing the number of proposed new satellite systems. Some of them have thousands of satellites envisaged in them. And you can see that a very large number of satellites is proposed to be launched through the coming decades. Now, I don't for one moment believe that all of these constellations will be approved or financed or actually launched, but even if only 10% of them are launched, you're still looking at another 6,000 satellites launched, which is actually a very significant increase over the number of objects already in orbit. Another issue that people worry about increasingly is that of spectrum interference, all these satellites interfering with each other. And this is something that is dealt with by the ITU and national spectrum management authorities. And I'll come back to that issue in a little bit later in this talk. Lastly, another issue that is of concern is the proliferation of counter-space capabilities. As more countries become critically reliant on space capabilities for their national security and defense, they will naturally want to be able to disrupt, deny, or degrade similar capabilities of potential adversaries. And so a number of counter-space systems are being developed, both terrestrial and space-based, and there is concern that the testing of such systems in space, if it produces debris, would be a cause of great concern to all other space actors. Okay, so that just sort of provides the context. Now let me go on to how we deal with space in the UN system. So discussions on space issues in the UN are carried out in 3 venues. New York, which is the General Assembly, Vienna, which discusses mostly the peaceful uses of outer space, and Geneva, which discusses the disarmament aspects and the frequency aspects of space activities. I mean radio frequency aspects. So if we start with New York, the General Assembly, the UN is structured in terms of a number of committees, and the committees that are relevant here for the purpose of this talk are the First Committee and the Fourth Committee. The First Committee deals with disarmament issues and security issues. The Fourth Committee deals with special political issues and a range of other things. And the peaceful uses of outer space falls under the Fourth Committee. But this immediately creates a kind of a dichotomy in the UN system and in multilateral space diplomacy about how these issues are dealt with, and the distinction between the two is becoming increasingly fuzzy. So the UN involvement in space activities, in space diplomacy began shortly after the launch of Sputnik, already in 1958, the UN established an ad hoc committee comprising 18 members. And this ad hoc committee was turned into a permanent committee of the United Nations in 1959 with 24 members. Again, the discussions in the early days of UN COPUOS were dominated by the two superpowers, and the other countries were there mostly as passengers. The committee has evolved in the decades that followed. This is a recent photograph of the Committee on the Peaceful Uses of Outer Space, or UN COPUOS as we refer to it. There are currently 95 member states with a very diverse range of technical capabilities and with different motivations for carrying out space activities. But COPUOS remains the principal international forum where states discuss cooperation and the peaceful uses of outer space. One of the most significant features of COPUOS is that it takes decisions on the basis of absolute consensus, meaning that every single state has to agree to every word in a document that is produced in 6 official UN languages. And as you can imagine, this can be very, very difficult to achieve. So what has COPUOS done? Well, over the years, it has produced a number of binding treaties that provide the legal framework for outer space activities. The foundational document is the Outer Space Treaty, and there are 4 subsequent treaties that elaborate on the fundamental principles contained in the Outer Space Treaty. But that is the kind of Magna Carta for space governance, and countries that have ratified this treaty, which is well over 100, domesticate their treaty obligations in their national law that governs space activities by their nationals and industry and so on. The UN has also generated a number of so-called soft law instruments. These are non-binding. They don't have the force of treaties, but they are politically binding on states. These are things like General Assembly resolutions or guidelines and recommendations. For example, here I show the UN guidelines on space debris mitigation. There are also guidelines. There's a safety framework, for example, on the use of nuclear power sources in outer space. And so, for example, the missions launched to Mars that have nuclear power sources on board would be in compliance with this international safety framework. The UN has also, over the years, carried out a number of world summits. I'm sure you're familiar with the various world summits that the UN has on things like sustainable development and so on. The UN has also organized world summits on space exploration and cooperation in the peaceful uses of outer space. The first of these was in 1968, and it really focused on international cooperation. The second started to focus on how to ensure that outer space is maintained for peaceful uses and building the capacity of states, especially developing countries, to benefit from space technology. And the third UNISPACE conference was carried out in 1999. And this started looking at space for human and environmental security and also concerns about preserving the space environment itself. Another function that the UN plays is to maintain an international register of space objects. Countries that launch satellites into space are encouraged, or if they are signatories to the registration convention, they are required by their treaty obligations to register their space objects with the United Nations. And so the UN maintains a register of all these objects that have been launched into outer space, which is important because it's not always obvious if you detect a space object who it actually belongs to, which country it belongs to. I only have time to describe very briefly the other activities of the UN in space. So in addition to space law, capacity building, and the progressive development and codification of space law, the UN has a program on space applications which supports developing countries in building up their capacities to benefit from space technology. It has also introduced a program on satellites-based navigation. So all the global navigation and positioning applications of space technology. Also, the applications of space for disaster management and relief, a program called UN Spider. The box over on the right shows the other areas that the UN Office for Outer Space Affairs is involved with and engages with UN member states to support them in their peaceful applications of space technology. So, I've spoken about peaceful uses. Very briefly, I want to touch on the disarmament questions. Those are dealt with in Geneva in the Conference on Disarmament. For a long time, there were concerns around the technologies for active debris removal, on-orbit servicing, and so on, because of their potential to be weaponized as counter-space technologies. There are also discussions around what's called the prevention of an arms race in outer space. There are ongoing debates about whether the way to deal with this is through binding treaties or non-binding instruments such as norms of behavior, and these are very much ongoing discussions. Geneva is also the forum that deals with the allocation of orbital frequencies and slots for the geostationary satellites. So those are fixed orbital positions of GEO, but it also deals with the frequencies of not only the GEO satellites, but satellites in all other orbits through a international coordination mechanism, which is implemented at national level by appropriate regulatory bodies in each country. So all these discussions get brought together back at the UN in the General Assembly, where every year the General Assembly adopts a resolution on the peaceful uses of outer space. And this is where this dichotomy between the first and the fourth committee sometimes affect things. You have diplomats, different sets of diplomats discussing issues that are cross-cutting, but they look at them from very different perspectives in the disarmament and peaceful uses communities. And this is one of the challenges that the UN will have to address, because the boundary between these two communities sometimes is a bit fuzzy. Also, the UN will have to find ways of engaging more fully with the private sector actors than it has in the past, because space is no longer a preserve of just governments and government agencies. So there are a number of solutions that are investigated. The UN doesn't do technical work, but it can use the results of technical experts to propose technical standards and guidelines for states to follow. So there are obviously technical solutions for a number of issues. And then there are also policy and regulatory approaches. Recently, the UN concluded a process of negotiating a series of 21 guidelines for sustainable activities in outer space, which was a very significant step forward. Also want to end quickly by talking about the importance of norms of responsible behavior. At the moment in space, we don't really have norms for responsible behavior, so folks can do pretty much whatever they want in many cases. So this is a terrestrial analogy where you see there's a street scene with a red traffic light. People have stopped waiting for the light to change, but you see one cyclist here in the blue shirt just kind of ignores that and advances, and so it causes problems. The situation in orbit at the moment is that I'd like to use a terrestrial analogy. Imagine you drive a car and you keep driving it until you run out of gas or it breaks, and then you just leave it on the freeway, you abandon it there. Well, that's pretty much what's happening in space right now. And in the early days of the space age, it didn't really matter much, but now it does matter. And so I think governments will start moving towards requiring licensees of space activities to remove their objects from orbit very soon after their useful lifetimes in space, so as not to create dangers for other users of outer space. Just want to end with also the remark that we need rules of the road. This is a movie of that was taken in 1906 in San Francisco, just in fact, as it happens, just a few days before the great earthquake of 1906. And you can see this kind of suggests what the situation is like in outer space at the moment, where you have different actors with different kinds of capabilities in terms of maneuverability, situational awareness, and so on. and it can cause a lot of chaos and uncertainty. And so it's important for the international community to develop rules of the road for behavior in space. I just want to end with this observation that there are a mixture of binding and non-binding ways of dealing with these things, with these challenges that I've described. They range from things like voluntary guidelines to transparency and confidence building measures to international codes of conduct. And these kind of create the conditions that ultimately could lead to more binding requirements such as a treaty. So I'll end there, and thank you very much.
Thank you. That was wonderful. I think we have just maybe 2 minutes for question and answer. Daniel, have you been monitoring? I know there were some.
Yes, yes, 3-4 minutes.
Okay. And I know there were some questions that were already answered in the Q&A. Were there things, and I haven't been monitoring the chat. Are there questions in there or?
No, I think all questions were posted in the Q&A window, and it seems that they've all been answered. So if nobody else makes any questions, we can go ahead and wrap up.
Well, if I could pose just a really quick question. Todd, are you still on? I was just curious about the microphones. Do we know why they failed with the previous rovers?
Yeah, so actually the missions failed. So the microphones would have worked fine. So it was just a mission failure. And of course I was being a little facetious, but the fact remains. So we're excited to, I think one of them might've been a Planetary Society, you know, advocacy funded, you know, private citizen funded effort to get a microphone on one of the missions. And I felt bad for him that the mission failed, but staying cautiously optimistic for February.
Awesome. Well, it's good to hear that the microphones are robust. We do have one question that was just posted in the Q&A from Terry Trevino. The Artemis Accords were recently agreed to. Do you think that the Chinese will jump in? Peter, do you want to take lead on that one?
It's a very interesting question. We've been wondering the same at Secure World, and it remains to be seen how they will react to this. I think it's still very early days, and countries are sort of digesting what the Artemis Accords mean. I think that the Accords certainly are going to stimulate some very interesting discussions around responsible behaviors in outer space and how we can use exploration as a way to encourage responsible behaviors by other actors. I just noticed in the chat there was a comment about the real challenge being traffic management. Yes, that's true. Space traffic management is something that it's a problem that we will have to solve. But I just want to emphasize that this is a problem that cannot be solved by one country alone or even a group of like-minded countries. This really is a multinational issue. Even if you talk about satellites having AI on board, all this kind of stuff, it really will need to have some international discussions. My guess is probably it will start being implemented at national level, and we have to see what are the best practices, and hopefully those best practices can then be proposed to the international community and adopted more widely.
Excellent. Unfortunately, I think that we are out of time. This has been a great session. I want to thank everyone for joining us, and to thank Peter and Todd for excellent presentations. This has been a really fascinating session. So I hope to see you guys in the next panels that are, I think we have a 10-minute break and then the next one starts. Is that right?